This is mathheals.com, where you can find more links to math YouTube videos and computer science. Well, in this lesson, we're going to take a look at claims dealing with two population standard deviations. Now, requirements says these samples are obtained using simple random sampling or through a randomized experiment. Samples are independent. Populations from which samples are drawn are normally disputed. And we're going to use Fisher's F distribution in this section. And this says if our population variance, sigma sub 1 squared, is equal to sigma sub 2 squared, and S, remember, is our sample variances. So S sub 1 squared and S sub 2 squared are sample variances from independent simple random samples of size n1 and n2 respectively, drawn from normal populations. Then F is equal to S sub 1 squared over S sub 2 squared. Follows the F distribution with n1 minus 1 degrees of freedom in the numerator and n2 minus 1 degrees of freedom in the denominator. We'll come back to these steps. So let's skip down to our first problem. And it says, find a critical value for right-tailed test. Not that I need the picture, but let me just draw it to really emphasize the right tail. Alpha is 0.05. Degrees of freedom in numerator, I'll say NDF for numerator degree of freedom, equals 20. And denominator is a degree, and degrees of freedom in denominator, DDF, is 25. And it says want to find a critical value. Well, this is a little piece of the claim process. So let's skip up here to the part where we find the critical values. Now we got a right tail, so we're going to use this right here. And it says our right critical value is equal to, and I'll put this notation here, F alpha, and then N1 minus 1, and then N2 minus 1. Well, alpha in this problem was 0.05. N1 minus 1, that's our numerator degree of freedom. And we've already subtracted 1 from that. That's when you got a degree of freedom, that's always already subtracted. So this is 20, and this is 25. So again, this is the numerator degree of freedom, and this is the denominator degree of freedom. And let's see what our critical value would be. Okay, numerator degree of freedom was 20. Numerator degree of freedom is cross top. Degrees of freedom in numerator. Well, this is 1 through 8, so that's no good. Go to the next page. Well, here we have 20, but the denominator degree of freedom is 25. The denominator degree of freedom is on the left side here, and this only goes to 8, so that's no good. Let's go to the next page. That's obviously not any good. Okay, this one I think will work. Yeah. Okay, so our numerator degree of freedom is 20. So let's look in this column dealing with 20. We're going to look right here. Okay, and then we're going to go to our denominator degree of freedom of 25. So I'm still in this column. I'm scroll down, and here's 25s. Well, this is the start of the numerator degree of freedom of 20, and then 25 for denominator. Now our alpha is 0.05. So I come over here, I look up 0.05. See the 0.05 there? And I would use 2.01. And that would be our value we're trying to find. Okay, let's look at our next example. Find critical values again. It says find a critical value for a left tail test. So we got left tail. It says alpha is 10%. Degrees of freedom in numerator. Numerator degree of freedom is 6. Denominator degree of freedom is 10. Okay, so let's find our critical value. Well, we're dealing with a left tail here, so I'm going to go to the left tail formula. And this says that we're going to use 1 over f alpha, f sub alpha, and then n2 minus 1, and then n1 minus 1. Well, this flips around. This puts a denominator degree of freedom first. So we're going to look up f alpha was 10%. Then our denominator degree of freedom is 10. And then we're going to look up 6. So those get flipped around when you're done with the left tail. Okay. So we're going to be looking up 10 and 6. So we're pretending, or we switch these around. So this is our numerator degree of freedom. So we're looking up 10. That doesn't have 10 on there. This has 10 on there, but this starts at 9, and I need 6. So we'll go back one more. Here's 10, that'll work, and 6. Okay. Like I said, we flip these around, so we're going to use 10 for our numerator degree of freedom, because it's the left tail. So we're looking in this column. This one right here. And I'm going to scroll down. I'm looking for 6. So this is the start of numerator degree of freedom of 10 and denominator degree of freedom of 6. And I'm looking for alpha of 10%, which actually is this one right here, isn't it? So 2.94. So our critical value is going to be 1 over 2.94. Let's see what that gives us. 1 divided by 2.94, 0.34. Okay, let's look up or do our next problem. It says find critical values for a two-tailed test. Okay, so we have two tails with alpha is equal to 0.05, and numerator degree of freedom is 5. So numerator degree of freedom is 5, and denominator degree of freedom is 8. Okay, let's go to our sheet now, and we got two tails. Well, let's find our left critical value. So our left critical value, that says we're going to have 1 over, and then we'll look up the value from our table, and it's alpha divided by 2. Well, alpha is 5%, so we're going to look up 0.025. And then, let's see, this is left tail, so we've got n2 minus 1, so that would be 8. And then we'd have our numerator degree of freedom. So you swap those around. And that's the value we're going to look up. Okay, so 8 and 5. 8 and 5. Here's 8. Always the number that's first. For example, 8 is first here. That's your number across top. And then 5, so we'll scroll down. Here's the beginning of the 5s. And what are we looking up for alpha? 0.025. 0.025 is the third one down, which 0.025 would be this one, 6.76. So this would be 1 over 6.76. So 1 divided by 6.76. And we get 0.15 if I take it 2 decimal places. Okay, now let's look up our right critical value. See what our formula says for that. Again, we're looking at the two tails. Don't look up under the right tail up here. So Two tails, the right critical value says F alpha divided by 2, so we're going to look up 0.025, and then N1 minus 1 and N2 minus 1. So that's just your 5 and your 8. You don't flip them around on this one. So let's see what that gives us. 5 and 8. Well, here's 5, so we're looking in this column. And 8 is down to... Okay, here's the start of it. And the alpha we're looking up is 0.025, which is the middle one, which would be 4.82. Well, I can't highlight it, but hopefully you see it. 4.82. And those will be our true critical values for a two-tail. Let me save that. What's this one called? Depopulation. Two population standard deviations. So best deviation page 01. There we go. Yeah, let's look at an actual claim now. Number 4. It says, test the hypothesis that sigma sub 1 is not equal to sigma sub 2. So that's our claim. Sigma sub 1 is not equal to sigma sub 2. At alpha is equal to 0.05. And first population, N1 is 8. So N1 is 8. And S1 is 3.3. For our second population, the sample was 6, so N2 is equal to 6. And S2 would equal to 3.6. Okay, so that's the information they give us. Okay, so let's go back up. And we're going to use a classical approach here. So now we'll go through steps I mentioned, but I didn't show. Step 1, write down a shortened version of the claim. Well, we did that already. Step 2, come up with a null and alternate hypothesis. H naught always has the equals part on it. Well, this is a not equal to. So we're going to put the not equal to on H1. Now, the only symbols that can go on H1 are less than, greater than, and not equal to. So the fact that this was a not equal to, the only place we could put it was H1. Now, our claim matches H1 since the symbols are the same. That's step 3, actually. Now, our H naught. If this is not equal to, then this one is going to be equal to. These are opposites of each other. So the only symbols you can put on H naught are less than or equal to, greater than equal to, or equal to. Now, I like these to be exact opposites of each other, but a lot of textbooks are making this so this is always equals. So something to keep in mind for your particular textbook if you're not in my class. I like these to be exact opposites. Just clicks better with students, I think. Okay, we did step 3. Step 4, draw the picture and split alpha into the tails. Not equal to on H1, not equal to on H1 is 2 tails. Okay. So we're going to have a critical value here, and we'll have a critical value here. Split our alpha into our tails. Alpha is 5%, so put 0.025 here and 0.025 here. Now all of it adds up to 100%, so 5% is in the tails. This has to be 95%. Okay. Next step, find the critical values. Well, we got 2 tails, so let's find our left critical value. I'll do some of the work over here. So left critical value tells us it's going to be 1 over. I'll look it up in our table, the F distribution, and alpha divided by 2. So 0.025, comma, and then N2 minus 1. Well, N2 was 6, so 6 minus 1 is 5. And then N1 minus 1. Well, N1 is 8, so subtract 1 from that, and that gives you 7. So let's go see what that is. Okay, 5 and 7. I'm going to find 5 across the top. Here's my numerator degree of freedom. That's always the first number you have in here, besides the 0.025. And then 7. So I'm gonna go, this is the column I'm looking in. I'm going to go down to the 7s, which starts right here. And we want alpha of 0.025. So 0.025 is the middle one. So 5.29. Can't highlight it, but that's weird. Anyway, 5.29. So this will be 1 over 5.29. Assuming my eyes didn't get off. So we'll do 1 divided by 5.29. 2 decimal places, 0.19. So this one is 0.19. Okay, now our right critical value from our sheet, it says F, and it says alpha divided by 2, so we're going to look up 0.025 again. And then N1 minus 1, well, N1's 8, so we put 7 here. And then N2 minus 1, which was 6. 6 minus 1 is 5. So let's look that up. So we got 7 and 5. So I want 7 across the top and 5 across the side. So I'm looking in this column. Oops. Looking in this column. And going down to the 5s. And I think we're looking at 0.025 again. So 6.85. So that would be this critical value. And where's my PowerPoint? There it is. Okay, now we're going to find our test statistic. And actually, I put that on the next page. I should have deleted this. Okay, let me delete that. Sorry about that. Still a work in progress. So our test statistic says use 2-samp F test on a TA3, TA4. We'll do it with technology, and we'll do it by hand in the same video here. Sometimes I split those up just because I don't want the video to become too long. So it says we're going to use 2-samp F test. So let's go see what that entails. Okay. So I press my stat button, go over to tests. Up arrow will probably get to it faster. And see, I have 2-samp F test. So I choose it. Now, if you're given raw data, of course you want to choose data, and it'll probably ask you to put one of the set of data in L1, one in L2. We got summary statistics. So if it isn't already highlighted, right arrow over, put your flashing cursor on stats, and press enter. Then down arrow, X1 is S1, which is 3.3. N1 was 8. And S2 was 3.6. And N2 was 6. Okay, the symbol on H1 was a not equal to. So I'm going to put my flashing cursor on not equal to and press enter. And then I'll down arrow to calculate and press enter. And our F equals is our test statistic. So we got F is equal to 0.84. Now I'm going to go ahead and write down the p-value on this also. We'll get back to that. P-value was P equals 0.8031, 0.8032. There we go. Large p-value. Okay, now let's find our test statistic by hand. Okay, this is our formula. It says F naught, but you can do F naught. You want to take your S1 squared. That's our variance, sample variance. So S1 was 3.3. So we have 3.3 squared over, and then S2 squared, which was 3.6 squared. So 3.3 squared divided by 3.6 squared. And we get 0.84. Oftentimes a test statistic isn't actually that hard to find by hand, but calculator makes it a touch easier. Okay, so now we got our test statistic. We're still doing the classical approach, so this says, see where it falls. This is a number line. Here's 0.19, here's 6.85. 0.84 would fall somewhere in here. So for our conclusion, it says if test statistic falls in the main body, which it does, you accept H naught. If we accept H naught and H1 are opposites of each other, that means we'll reject H1. And since our claim matches H1, whatever we say about H1 is what we say about our claim. We rejected H1, so we'll reject our claim. Now, most books will not use the word accept. I like to go with accept and reject because it seems to click better with students. Accept is a pretty strong word. The word they'll use is do not reject. So keep that in mind when you're looking at your particular book. Okay, now that's the classical approach. Let's talk about the p-value approach. I won't actually solve it because it's pretty straightforward. I actually like the p-value approach the best of all on these because when you're using tables, you'll find that sometimes you have to go to the nearest numerator degree of freedom or nearest denominator degree of freedom. Sometimes that's pretty far off. Like if you have n is equal to 2,000, well, the nearest one is n is equal to 1,000. So that's pretty far off. Your p-value approach using technology is using numerical methods, and it has more precision. So that's what you should use. Okay, our p-value approach. Write down a shortened version of the claim. Well, that's what we did there. Come up with a null and alternate hypothesis. H naught always has equals part on it. Well, that's what we did there. See if your claim matches H naught or H1. Well, it matches H1. We did that already. Find the p-value. And we'll use technology, 2-samp f-test. And using 2-samp f-test, then we get our p-value is equal to this right here, 0.8032. Then it tells you to compare that against alpha. If p-value is greater than alpha, which it is, alpha was, I don't know what it was, 5%. There it is. Alpha is 5%. This is obviously greater than 5%. So if p-value is greater than alpha, accept H naught. So we get accept H naught, we reject H1, and reject claim. The benefits here, even though you get same answer, is this is precise because this is using numerical methods to get this. Where here we'll have to do some rounding with the critical values to go to whichever one's closest, which may skew the results. Let's look at our next example. I think I got room here. Number 5. Says, test the hypothesis that sigma sub 1 is greater than sigma sub 2 at alpha is equal to 0.05 level of significance for the given sample data. So alpha is equal to 0.05. So our first population, n is 22, so n1 is 22. S1, our sample standard deviation, is 4.2. For N2, our second population, N will be 12. And S sub 2 is equal to 4. I guess that's everything they give us. So let's go back up there and do the classical approach, wherever that's at. Here it is. Okay, write down a shortened version of the claim. We did that. Come up with a null and alternate hypothesis. Well, this is a greater than. The only place you can put a greater than is on the H1. Now, if that's a greater than, these are opposites of each other. This one will be a less than or equal to. Again, most books will put an equals here. Step 3, see if a claim matches H0 or H1. Greater than, matches H1, obviously. Step 4, draw the picture and split alpha into the tails. Okay, well, we got a greater than on H1. I come here, greater than on H1 means we have a right tail. Split alpha into our tails. Well, alpha is 5%, so put 5% there, and if 5%'s there, then 95% is over here. Okay. Find our critical value. And we got a right tail, so I'm going to be looking here, and it says for our right tail, our right critical value is going to equal to F alpha, which was 0.05. I'm looking at this alpha right here. And then N1 minus 1. N1 was 22, so subtract 1 from it, and I got 21. And then N2 minus 1. N2 is 12, so this would be 11. So we're looking up 21, 11. Okay, 21, 11. It's going to be as good as it gets. 21 isn't in my list. Closest value is 20. So we'll come here. We're going to look there. And then we'll look at 11 for our denominator. Well, there is no 11. It's halfway in between these. If it's closer to 1, like if I had 14, I'd go to 15. If it's closer to 12, like 11 or 13, I'd go to 12. If it's halfway in between, then you'll average them. Okay, so here we're going to 11 is halfway in between 10 and 12, and we're looking up 0.05. So the 0.05 on this one is I can't highlight it there. 2.77. So I got 2.77, and the 0.05 on this one is 2.54. Why can't I highlight that? There it goes. So plus 2.54 and divide by 2. Now some books will tell you just to go with the range. They'll say the critical value is somewhere in there. We don't know exactly where. This particular book we're using says average them. This particular section doesn't seem to be a whole lot of consistency in different books from what I can see, which I don't particularly like. I like consistency. So 2 decimal places, if I add those together and divide by 2, I get 2.66. Now averaging this is probably going to be good enough, but it's not perfect because of the distribution. Now, I don't got our picture here, but let me go back to our picture. The way the graph is shaped, finding the average of it isn't a perfect solution. I actually like the other books better, where they say we don't know what the critical value is, but somewhere between 2.54 and 2.77. But we'll go with this. Only time it really matters if your test statistic fell is somewhere in this range. Okay. Our test statistic. And we're going to find it 2 different ways. We'll find it with technology, and we'll also find it by hand. So I cover both cases here. And with TA3, TA4, it tells us to use 2 SAMP F test. So let's go do that. So press Stat, go over to Tests, up arrow to 2 SAMP F test, and press Enter on it. And we got summary statistics again, so I'm going to leave that highlighted. S1 was 4.2. N1 was 22. S2 is 4. And N2 is 12. Assuming my eyes didn't get off and I got everything entered correctly, the symbol on H1 was a greater than. So I'm going to go over and highlight greater than and press Enter. And down arrow to calculate and press Enter. And our F equals our test statistic. So we got F is equal to 1.10. 1.1. Now since I'm here, let me go ahead and write down p-value, because we're going to be talking about that here in just a second. P-value is 0.4498. Okay. Yeah. And by hand. It says we're going to take our sample standard deviation of our S sub 1 of our first population, square it. So that'd be 4.2 squared over, and then 4 squared. Our second sample standard deviation. Let's see what that gives us. 4.2 squared divided by 4 squared. 1.1. Okay, so this is the number line. Here's 2.66. F point or 1.1 falls over here somewhere. So let's see about our conclusion. If test statistic falls in the main body, it says accept H naught. So we'll accept H naught, which means we'll reject H1. And since our claim matches H1, whatever we say about H1 is what we say about our claim. So we'll reject our claim. Now for our p-value approach, if we were using that approach. Write down a shortened version of the claim. Same step there. Come up with the null and alternate hypothesis. Same step there. See if your claim matches H naught, H1. Same step. Find a p-value. Use 2 SAMP F test. Well, we did 2 SAMP F tests, and we found p is equal to 0.4498. Then you're comparing that to alpha. Alpha is 5%, 0.05, so this is greater than. This says if your p-value is greater than alpha, you accept H naught. So we accept H naught, reject H1, reject claim. So that's how you do the p-value approach. And again, I would emphasize to use the p-value approach. Because remember when we found this critical value up here, it wasn't perfect, was it? Now, it really doesn't matter because our test statistic wasn't even close to it. But again, you get some kind of iffy results when you do that. Let's save this, and then we'll look at our last problem. Okay. Our claim. Sigma sub 1 is less than sigma sub 2. At alpha is equal to 1% for the given data. And for our first population, n is 11, so n1 is 11. What am I doing? N2 S1 is 5. Now I do N2. N2 is 8. And S2 is 7.2. Okay. Well, let's go through our steps for the classical approach. Write down a shortened version of the claim. We have that. Come up with a null and alternate hypothesis. The only place you can put less than is on H1, so that's where this has to go, which obviously implies that the claim then matches this. Well, if that's less than, then this one has to be greater than or equal to. And again, the books will always put equals here, our current textbook. I like this. These are exact opposites of each other, because if you reject this and you accept this, they should be opposites of each other, in my mind. Gives you the same result, though, in case you're wondering. See if your claim matches. We already did that. Draw the picture. Well, less than on H1. Less than on H1 means the left tail. So left tail. Split our alpha into our tails. So we got 0.01 there and 0.99 here. Okay. And we got left tail, so I'm looking at this top one now. It says left critical value is equal to 1 over F alpha N2 minus 1 and N1 minus 1. So this will be 1 over F alpha was 1%. N2 minus 1. N2 is 8, so 8 minus 1 is 7. N1 minus 1. N1 is 11. 11 minus 1 is 10. So let's go look that up. So 710. 710. Here's 7, but there's no 10. Chi-square. Okay. There it is. Okay. Here's 7, so we're looking in that column. And then 10, so this is the start of where we're going to be looking. And we're looking for alpha of 0.01. Alpha of 0.01, assuming my eyes didn't get off, would be 5.2. So this is 1 over 5.2. So 1 divided by 5.2, 0.19. So this critical value is 0.19. Okay, now let's find our test statistic. And we're at step 6 now. For TA3, TA4, it tells us to use 2-sample F test. So let's go see what that gives us. Grab a drink here. Okay. So press stat, go over to tests, up arrow to 2-sample F test. Press enter on it. We want stats, so down arrow. S1 was 5. N1 was 11. S2 is 7.2. N2 is 8. The symbol on H1 was a less than, so I want to write arrow over to the less than, press enter on it to highlight it, down arrow to calculate, and press enter. And we get 0.48. I'll write down the p-value because we'll come back to it shortly. P-value is 0.1427. I made these numbers up. It seems like every p-value we've done with these examples has been larger than alpha, but oh well. Okay, let's do this by hand for our test statistic. It says by hand, we're going to take S1 and squared over S2 squared. S1 is 5, so we got 5 squared over S2, which is 7.2 squared. Okay, so we got 5 squared divided by 7.2 squared. And we get 0.48. Okay, so here's the number line, here's 0.19, 0.48 will fall over here somewhere. So for a conclusion, yet again, our test statistic falls in the main body. They won't always do that, but if test statistic falls in the main body, you accept H naught. So we accept H naught, which means we reject H1 because they're opposites of each other. Now our claim matches H1, so whatever we say about H1 is what we say about our claim. So we'll reject our claim. And p-value approach. Okay, write down a shortened version of the claim. We did that. Come up with the null and ultimate hypothesis. Did that. See if your claim matches H0 or H1. We did that. Find your p-value. And again, we use a 2-SAMP F test, and that gives us our p-value. Now, notice this is exact. Excuse me. This is done through numerical methods, so there's no rounding to the closest one. This is exact. So we got 0.1427. And step 5, if p-value is greater than alpha, alpha I think was 1%, 0.01, so it's greater than, it says you accept H0, which we got accept H0 here, reject H1, reject claim. So you get your same conclusion, but with precision. So let me save that. There we go. And then stop the recorders.